Well, we already know a lot about aldehydes and ketones, which is what we're covering in Chapter 19. We've seen them produced by certain reactions. We have learned that they have a large dipole, and so they're polar, and nucleophiles can attack the carbonyl, the carbon in the carbonyl. We learned last semester the hydration reaction, and this semester we've done Grignard reaction with aldehydes and ketones. We're going to learn a little bit more about them, review the old reactions, and then learn a few new reactions. First of all, I want you to remember that we can tautomerize aldehydes and ketones. It is an equilibrium that usually favors the carbonyl. How does tautomerization occur? This hydrogen comes off and is attached to the oxygen in the carbonyl, and then the double bond moves down here to between the two carbons. To practice this, what I want you to do is draw the enol form of 3-methylbutanal. Okay, 3-methylbutanal looks like this. To draw the enol, we're going to take the proton off the alpha carbon here and put it on the hydrogen and move the double bond down between these two carbons. And that is our enol. Can you write the enol form of 2,2-dimethylbutanal? Well, this is 2,2-dimethylbutanal. Can we form an enol? No, we can't. There's no hydrogen here on the alpha carbon. The alpha carbon is quaternary. No proton is there to move. So you cannot form an enol when you don't have a hydrogen on the alpha carbon. Keep that in mind in future reactions because you'll have to recall this when we are doing reactions. So what is an enolate? Well, this is just a proton has been removed from an enol, and so we have the anion of the enol. To draw an enolate, the first thing you do is you draw the enol of whatever carbonyl you have, and then remove the proton from the alcohol portion. So here's an example of how you would draw the enolate of cyclohexanone. Here is cyclohexanone. The enol of cyclohexanone is this. What's the enolate? Just remove the proton. And we'll be seeing that in some reactions, the enolate is very important. So what is the enolate of cyclopentane carbaldehyde? Well, this is cyclopentane carbaldehyde. To form the enolate, we just have this. For the aldehyde to be formed, what can we do? We've already learned several things. We learned last semester how to oxidize the primary alcohol with PCC to form the aldehyde. We learned you can't do it with chromic acid because that takes it to carboxylic acid. We learned how to do oxidative cleavage of an alkene, and you get an aldehyde when one of the carbons has a hydrogen on it. Only one carbon chain on one of the carbons. That forms an aldehyde. We learned this semester that you can do hydroboration of a terminal alkyne, and that gives you an aldehyde. What we are going to learn that's new in this chapter is how to form an aldehyde from an ester. Here are the old reactions. Here's a primary alcohol. PCC or PDC, it oxidizes it down to the aldehyde. Remember, don't use chromic acid. That takes it to the carboxylic acid. Here's an alkene. This carbon has a hydrogen on it. Whenever you have a hydrogen on an alkene, oxidative cleavage using ozone and zinc and acid gives at least any carbon that has just one hydrogen on it, it will change it to an aldehyde. Here's a terminal alkyne. Hydroboration, it gives an aldehyde. This carbon becomes an aldehydic carbon. Here's the new reaction. Reduction of an ester. Here is an ester. When we use lithium aluminum hydride, remember that last semester we learned that we cleaved this in half and changed this portion to an alcohol and changed this portion to an alcohol. But there's a way of stopping this reduction. We use something called diisobutyl aluminum hydride. Instead of writing out that horrid name, what we do is we call it DBA, or some places you see it written as DIBAL-H, DIBAL, then -H. It's exactly the same thing. This is a mild reducing agent that stops the ester at the aldehyde change. It limits the reduction up to the aldehyde. It won't attack the aldehyde. So what do we get? We get cleavage of this ester right here, and it changes the carbonyl side to an aldehyde, and it changes the alcohol side to an alcohol. So now what I want you to do is practice these reactions. There are 4 reactions using what we just learned. Try to figure out how you can do each of these and write down all the reactions that you would need to do, and then start the online lecture. So how can you form acetaldehyde from ethyl acetate? Well, the first thing we do is write down what is ethyl acetate. Now we need to form acetaldehyde. Here's acetaldehyde. What are the conditions that we need to go from ethyl acetate to acetaldehyde? Well, that's the new reducing agent we just looked at, DBA. So DBA followed by water gives us the acetaldehyde. How can you form 3,3-dimethylbutanal from 3,3-dimethyl-1-butyne? Well, this is 3,3-dimethyl-1-butyne. Here's 3,3-dimethylbutanal. You can see that this carbon right here became this carbon. What conditions cause that? Well, that would be hydroboration. To make hexanal from hexanol, here's our hexanol, here is our hexanal. What do we need to do? That's a reducing agent, but we can't use oxidizing agent. But we can't use chromic acid. What do we use? We can use PCC. How do you form hexane dial from cyclohexene? Well, here's cyclohexene, and if I write hexane diol, you can see how the carbons come from the cyclohexene. What happened here? Oxidative cleavage. So ozone followed by zinc and acid gives us oxidative cleavage to the dial.